Hello, welcome to chapter 6. We're going to be doing, this episode 1, we're going to be just touching on simple harmonic oscillators. And so, what is a simple harmonic oscillator? Well, I'm going to have an object here, maybe like I have a wall. I'm going to have like a spring and a block, and then on some ground, and this is going to be frictionless, right? If I pull this, right, well, we're going to experience some tension force here, and that's going to be the spring force, right? So we can use Hooke's law. So F of our spring is equal to negative kx, and this is x is our displacement, and minus kx, and yeah, what's gonna happen is it's gonna come back forwards, it's gonna come here, it's gonna come here, and it's gonna to basically cycle back and forth, back and forth, back and forth, right? So we're going to look at deriving the equation of motion for this this is called a simple harmonic oscillator. So we start with our expression for force here. We get x double dot equals negative k over m times x. And so we can move these to one side, x double dot plus 0 plus k over mx equals 0. And what can we do? Well, we can use the, this is a undetermined coefficients. Yes, so these are undetermined coefficients. We can use that technique for solving this differential equation. So what are we going to do? Well, we're going to say, okay, x is equal to e to the power of rt, and we do this and we get r squared e to the power of rt plus e to the power of rt plus r k over m e to the power of rt equals 0. All right. And what does that get? So this is actually x dot. This x doesn't go anywhere. I made a mistake here. This x is here. Okay, so what do we get from this? Well, we can separate this out. R squared plus k over m equals 0. And well, we find r is equal to the square root of negative k over m, which is equal to square root k over m times I, right? And then obviously plus minus, right? And so I'm going to use this substitution for frequency. Okay, it's equal to k over m, and this is going to be equal to plus or minus omega I, right? So if you remember what happens when we solve these, those are our roots. We can use the Euler Identity, e to the power of I omega t is equal to, so e is equal to cosine omega t plus I sine omega t. Right, and so these are the solutions for our x equals e to the power rt, x equals this, and then these are our solutions, right? Although obviously these aren't complete solutions because we need to have our coefficients for each one. So that's all well and good for now. Although we are going to make an assumption here where, because remember we have this plus or minus, r equals plus or minus, so we have this plus minus that we can consider. I'm going to do, so since x is a real number, it is equal to its own conjugate transpose, or not conjugate transpose, it's equal to its own conjugate, because it's a real number, because, you know. And as a result, this implies that, well, x is equal to c1, c2 conjugate, right, of cosine omega t plus sine omega t. And our I. So this implies that these two, since this conjugate's a real number, this means that c1 conjugate is equal to also this actually this I disappears when we, because we consider that part of the constant. This means that c1 transpose is equal to c2, and so we can use that. So if we pick these constants just appropriately, they will cancel out. So how are we going to get rid of these? Well, suppose we have, we're going to replace these constants with some b's, right, which are real numbers. Cosine omega t plus b2 sine omega t and x. Right, so suppose we picked an appropriate c1 and c2, and we're going to be left with this b1, b2 as our roots, or as our coefficients. So I'm going to draw a triangle here. It's going to be b2, it's going to be b1, and here is some angle theta, and here's going to be a. So what's going to come out of this is we have the identity a equals the square root of b2 squared plus b1 squared, and this is equal to a sine of, I'm actually going to set this as phi, which equals a cosine phi, right? And we have the alternative, which is theta, right? The concrete angle. And well, we can substitute these in terms of a, this radius here. So when we do that, we get a cosine phi cosine omega t plus a sine of phi sine omega t. And well, this doesn't seem to help. It just made things more complicated. But we can distribute this a to the outside. And if you remember, cosine of alpha minus beta is equal to cosine alpha, or yeah, cosine alpha cosine beta plus sine alpha sine beta, right? And so this, using this identity, becomes a cosine omega t minus phi. And if we did the opposite, if we did, so this is also equal to a cosine theta, a sine of theta, if we used theta instead. So the relationship between theta is equal to 5 plus pi over 2, or actually pi over 2 minus phi. That's the relationship there. But if we were to use theta instead, we would actually get this equals a, but basically the exact same identity, a sine omega t plus theta. And this theta or phi is going to be called, this is the phase shift phi or and theta. And so this is the defines the way our thing oscillates. And this A, what does this say? Well, this A is the amplitude, and this is our frequency. So let's graph this for a second. If we have our graph, here's 0. We have A minus A, and we have our, it's going to look something like something like this, where it goes up and then back down, right? And then obviously there's a gap, so this is our top of our amplitude, and it's going to go from 0 here. We have our period is 2 pi over our frequency. And the reason why this doesn't start at A is because we are taking away that phase shift, right? So this would be here minus that phase shift phi, and that's what our graph is going to look like. Yeah, that's about it. Thank you for watching.